My pleasure to introduce Kevin Luli from Yale. He's going to talk about fitting next functions to data from mathematician. Thank you.
Thank you for the invitation. It's a pleasure to be here again and to give this lecture. Okay, so to begin with, let me put you in a setting in which we can state the problems. So we're going with Cm of Rn. So it's the space of bounded n times continuously differentiable functions of Rn equipped with pointwise more. Okay, so it's a pointwise measurement of how big the function is for derivatives up to order m. Okay, so we need problems. So you can trace this back to 1934 as the following questions. Okay, so fix. Okay, so throughout this talk, integers m and we fix throughout this talk. Okay, so given the following arbitrary subset of Rn. So we are not assuming anything special about the set E. It's just any subset of Rn. A real value function on it. And we want to know whether there exists an f in Cm of Rn such that f agrees with little f on E. Okay, so that's the decidability problems. So if such an f exists, it's said to be an extension of little f or an interpolation of f, depending on whether you're a mathematician or a statistician. Okay, so if an extension exists, then you can ask further questions. Okay, so optimum norm problems, which asks how smart can we take subject to the condition that f agrees with little f and E. Okay? And moreover, what does f look like? Or more precisely, can we take f to the x linearly on little f. Okay, so that's the structured problems. And so all of these problems are going to be envisioned to have real life applications at the end. So in real life, the set we are given is a finite set. So in that setting, we are going to ask the practical questions. How fast can we compute f? So if E is finite, how fast can we compute capital F? So these are the questions that will be addressed in this talk. And
in problems Q2 and Q3, are you asking that in the context of the optimization problem, Q1, or just
Yes.
with some?
Yes, so I will state this just loosely define the problem at the moment. I will make the problem precise for you in a moment. Okay, so all right, so you can study this problem. Okay, so if you fix the function space, that's
why I asked the question. You said yes.
Y class. That's Y class of problems that you can study. So you can change the setting a little bit. So the other function space that we will work with, instead of Cm, you can work with Cm R1 Rn, which is subspace of Cm Rn. You put the standard norm. Highest derivative and this difference quotient. And look at where this is the biggest. Still, this is in this space you're measuring regularity in the pointwise sense. Okay? So other function space in which you can study this problem is the Sobolev space. So LMP Rn consists of m derivatives in LP. So you equip it with the semi norm. And some LP norms. Like that.
Where MNP are large enough so it has pointwise values?
Okay, so yes, so eventually so we will make that assumptions, but at the moment this is just the function space that we will work with. Okay, so first of all, so let me say a few words about why you want to study the Whitney's problems in the setting of Sobolev spaces. Okay, so if you let P tend to infinity, you recover the classical space. So this is just a direct generalization from a mathematical standpoint of view. But if you look at, so the Whitney's problems contains the Dirichlet problems as a special case. So the Dirichlet problems ask you to minimize the L2 norm of the energies, or the L2 energies, subject to the condition that this function agrees on a given set, which we can interpret to be the boundaries of some set. So analyzing this is equivalent to understanding solution to a differential equation. If you look at the Euler-Lagrange equations, it turns out to be the Laplacians. Okay? So this is just a specialization of the Whitney's problems for in this function space, one derivatives in L2.
The Dirichlet problem you would minimize the integral over omega, not over Rn.
Over omega, so it's a subset of Rn here. Okay, sure. Anyway, so it specializes to the Dirichlet problems. So you can study from the point of view of differential equations, but the point of view that we're going to take here is not from the point of view of differential equations. So we are going to construct calculus f directly from the given function f. Okay, so at least that tells you a little bit why the Whitney's problems in the Sobolev space could be of interest. So what do we know about the decidability problem? That is, this problem here. How can we tell there is such a function that matches with the given data? Okay, so this is handled by the so-called finiteness principle. Okay, so basically says that if you can solve the problems for finite sets, or bounded finite sets, then you can solve the original problems. Okay, so you can solve problems, meaning the extension problems, on bounded finite sets, subsets.
Finite sets always are bounded.
So I will tell you what that means. Bounded finite subsets is finite. It could be dependent on the size of the set E, but bounded means here is independent of the size of the set E. I'm getting it.
There's some estimates that depend on the diameter of the set.
I will make that precise. I will make that precise with an example. So if you can solve the problem on bounded finite subsets of E, then you can solve the problem with E. Okay, so let's just give you an illustration as to how this works. So let's work with the space of Lipschitz continuous functions on the real line, and the set E is some subset of the real line, and so here is a scatter plot of the theta values. Okay, now our task is to find a function in this function space, at the same time going through all of the points and minimize the Lipschitz norm, meaning that you want a function going through all of the points at the same time minimizing the slope. Okay, so there are too many points in the picture, so if there are only 2 points in the picture, the answer is obvious. Then you take a straight line going through the 2 points, that obviously does the job. So having 4 points is not going to make it more difficult. You're just going to connect any consecutive 2 of them with straight lines, and that will answer the problems. Outside of the, you're just going to extend it constantly. Okay, so let me just recap what has transpired. So in this process here, we learned how to solve the big problem just by knowing how to solve the 2-point problems. The set we are given is huge, could be huge to begin with, but as long as we know how to solve the 2-point problems, then we know how to solve the big problems. Okay, so this is the essence of the finiteness principles. So, in general, the following theorem is known. Okay, so let's say theorem Fefferman 2004. So given the following, there is this constant, okay, depending on how many derivatives that you work with, in which dimension you are in, such that the following goes. So, if for all subsets of E with no more than 8 points in it, there exists a function in Cm1 of Rn such that the function agrees with little f on S, and when you measure how regular it is in Cm1 of Rn, it is controlled by some constant m. So a point I want to make here is that the m has to be independent of which S that you look at.
There's no assumption with a small f?
No assumptions. So the only information that you get, that you see the appearance of the f is this f. It captures how irregular this function f is. So, but this case here, for instance, it doesn't depend on the little f. Okay, so under this condition, so what you can say is that
the little f is in CM space.
You're saying
No.
your hypotheses are, for example, going to immediately imply that f is continuous and so forth.
yeah. So the implication, yeah.
I was going to say, so what you're saying is that you can test whether f is differentiable or has an extension by looking at it restricted to finite sense of bounded subset.
Yes, exactly. So under this condition, so there exists an f.
I don't understood the quantization of capital M.
Capital M should come right after the capital K.
Capital M should come right after.
Yeah, when you say there exists an M such that, I mean, instead of saying M is independent of S, you could say
There exists.
Okay, so there exists a K and an M.
And m is just dependent on m and n?
No, it depends on F. It depends on F. Little F.
M of F. That's right, M of F.
Okay, so.
Right, nice.
Okay. So, alright, so there exists an F in CM1 of Rn such that F equals little f on all of V with a CM11 no bigger than some universal constant multiples of M. Of M of F.
Okay, so this M, as long as it exists independently of S, it's fine. So it's not that you're supposed to guess what M of F is based on the data for F.
Right, so you have to test for which F. You can always do it for this problem. For some M, maybe this problem you cannot find such an F for a given S.
Well, if f has an extension, there is an m.
Yes,
Clearly.
sure.
And so if there's an m that works for the entire set, the same m works for all the finite subsets.
Certainly.
And you're saying you go backwards.
Yeah. Okay, so this problem is here. So maybe
It's not stated right there. It's not stated right there.
You said it right.
It doesn't go into my brain yet, but it didn't go in.
it didn't go in.
Yeah, it didn't go in. So you did drill.
Wait, so
There's a square concept in a round brain.
what do you have to issue with?
Say it in words, man. Just say it in words.
Okay, so let's say I know this function f is extendable.
Yeah, sure.
Alright, so then there certainly exists a function with some finite constant m here. Okay? So then for any set here, s that you pick, certainly this is going to be true statement. So obvious, so it just, if this is true, certainly it implies that. But then it's going backwards.
Yeah, the role of M going backwards on my house one, right?
I give you m, and I want you to solve this problem. It may not be solvable, and in which case, this is a vacuous condition. But if you can increase the m eventually. If there is a solution, then you will find it.
Maybe it would help to look at the Lipschitz graph you drew over here. Remember,
Yeah.
two adjacent points, if you have some slope m between them.
Oh,
then
so
the local
let me-
extension has the same m.
So if
Oh, I
you,
get it. That doesn't work.
the local slope,
That doesn't work for little problems. Works for the big problem.
Yeah.
Exactly.
Okay.
If there exists m of f and for all s.
Dennis, even though it says there exists there, it's still given that there exists.
okay, so let me state the problem a little bit more precisely for you. Precise problems. That we are looking at.
Given.
Is there still a problem with this?
Well, I think what confusion was that the given also refers to there exists. It's given that there exists this
Yes.
information.
Yes.
That was the problem. That's what people were confused by.
Okay.
I'm just letting you know.
Alright, we don't have a logician on staff that helps you out. Sort of a psychologist.
Okay, so let me print the problem in a little bit precise form to look at. So given an arbitrary subset of Rn, and a real valued function on it, and the function space that we work with is either Cm of Rn Rn. Okay, so we want the following. This is just the extension property that f, when you restrict to the set E, it needs to equate with little f. And moreover, we are looking for f that optimizes the norm up to some universal constant. Meaning the only thing that is allowed to depend on is how many derivatives that you look at and in which function, in which Euclidean space you are in. Okay? So this version is more sensible because we are looking at the in. So if you just have this be equal to 1, this may not be a sensible question to ask. Okay? So we are solving the problems in this setting. Okay, so that's one situation in which you can check whether there exists a solution or not. Is by checking these conditions here. So this condition, if you look at a few points, is an easily checkable condition. Okay, so it's not a useless theorem. Okay, so now, so it works with this function.
Why is that? I mean, so the extension fs, depending upon s, you don't, unless you have an algorithm for constructing it.
We do.
How is it? So there's.
So for this finite problems, if you are dealing with a finite set, it's very easy to do. Let me just say that there is it's just linear algebra problems coupled with some inequality that you have to satisfy. But if you're dealing with finite set, it's just a linear programming problem that's easily solvable.
Is it possible to relate this solved that some problem of extension is solvable if and only if the same problem is solvable for all finite sets, subsets of this set?
Uniformly. So this uniform has to.
What is the uniformity? This?
Yeah, sure. Yeah, sure. That's stronger than this statement here. If you just this only says that you only need to sample set of finite size or bounded size. So bounded means that it's independent of the set I'm given. Okay. All right.
Like for the Lipschitz, you need 2 points.
You need 2 points, exactly. Yep. Okay, so we know that there is a finiteness principle. So this thing here, this constant here is called a finiteness constant. This statement here is referred to as a finiteness principle. Now, you can play the game with the function space Cm instead of Cm1. So it's a little bit bigger and things there are a little bit irregular. Okay? So in that case, this statement is, so if it's a finite set, so if E is finite, but it could be big, there could be a million point in it, but it's a finite set. Then the same statement, the same theorem holds for Cm of Rn. Okay? So the same theorem, let me refer to this as the finiteness principle. Okay, now, what about the infinite set?
What is that phrase you put in quotations there? What is it?
The same theorem, it means that theorem.
I understand that.
Finiteness principle.
Finiteness principle, okay.
Okay? So, alright. But, for a general set, there's no finiteness principle. For Cm of Rn. So it depends severely with what function space that you work with, in addition to the kind of set that you work with. So how do you see that?
It's because there exist Lipschitz functions that are differentiable.
Exactly. So, okay, so if you look at, let's say, the following functions. So less than 1 is just the absolute value function outside of this bounded smooth. Okay? Now, if you sample any finite numbers of points on it, I have to have knowledge on it. Okay, so as long as I sample a finite number of points on this graph here, notice that this graph is just Lipschitz continuous. But if you sample finite numbers of points on it, I can always fit through them with a C1 curve that is basically round out the origin here, and that goes through all of the sample points. It has to be finite. And this red curve here, if you measure how smooth it is, you can make it so you can fit a C1 function through it with a C1 norm no bigger than 10. Independent of how many finite points that you sample from the graph, I can always do it for you. Okay, but there's no but certainly it's not a C1 function that agrees with the entire function on the entire real line. Okay, so no finiteness principle here, meaning that finite point is not enough to pin down just the behavior at the origin here for you. Okay, so the decidability problem, that's how you tell whether there exists a function in a smooth class of Cm and Cm1 is in good shape. So I can move on to tell you how you construct extension and how the extension look like. But I think I will take a detour to show you how the finiteness principle is related to an algebraic geometry problem that is of recent interest to people. Let me, before I forget, I should say the history of this result here. So, this was first conjectured by, okay, so let me go back to here. So, Luli published last month. 2001. Proved the finiteness principle. For C1, 1, or n, with the constant C1 n equal to 3 times 2 to the n minus 1. So meaning if you look for one derivatives that's Lipschitz continuous on the plane, if you know how to do the problems with 6 points, then you know how to do it for the entire set E, any set E. Okay? So actually this constant here is shoved. In their proof, they show you that it's shoved. And so based on this, they made this conjecture. And in 2004, the Fefferman proved the conjecture. So it resolved Whitney's original problems. Okay, so how does this?
What's the constant that relates the m and the in this case?
In which case?
In this case, the m. How close to the optimum?
The m depends on the function you give me. The m.
The ratio.
The ratio here.
The capital M, you said.
Yeah.
So the capital M depends on the function I'm given on f, right? So you can, okay, so I can define this m.
So the m, but the CMF is
Okay, so let me put it this way.
CM, oh, but yeah, what is CM? Yeah.
Let me put it this way. So you can take m to the unit of C.
If you more words to
With E Cm1.
Now I want to know their theorem. What is the C?
What is the C here?
Yeah. Does it have a concrete thing for this A? What's the C?
It's some exponential function in the end, in m. So I cannot tell you exactly what it is.
Exponential.
Yeah, exponential.
In the end.
Yeah.
Is there improvement of that in the case when E is compact?
E is compact.
Yeah.
Yeah.
Is then possible to improve somehow? Okay, so probably it's not a good time.
Okay, so this thing you will always compactify the first, restrict to a cube. So being compact or not,
No,
essentially no.
It's impossible. Take half a line, open set. Open set is okay. There you go.
Okay. So this is problems that's studied recently by the algebraic geometry. Over Brenner's, now in Hochster. Oxford like that? Is that right?
Yep.
Okay. And now it's Kollar. Okay, so the statement of the problem is as follows. So let the function space be either Cm1 or Cm on Rn. Okay, so I give you d real valued functions and another real valued function on Rn. So the question is, can you find f1 to fd in the function space x such that G has a linear combination of the Gi with the Fi as the coefficients? Is the statement clear? Alright, so how can we tell there's such a thing? Well, first of all, if every function that I mentioned here is polynomials, then this is an easy problem. We just ask you to decide whether this G is in the ideal generated by a Gi. So you can use the group for the basis, for example. But so in this general setting, so what do we know about it? So if you work with the space of continuous functions, then Fefferman and Kollar-C solve the problems. In 2011.
Yes.
No, it just asks you
No, it's
to
yes.
No. It's not a yes or no question.
Yes, it's an algorithm for deciding if it's yes or no.
Yes, it's an algorithm for deciding a yes or no question. As it stands, it asks you to decide whether there exists such a thing. It doesn't. It's not a yes or no question. Well, it is. It's being considered.
Is there an algorithm? There is an algorithm.
Yeah. Or is there a way to tell?
Yeah.
So you want to come up with some kind of criteria for it. But back then, when they wrote this paper, they left it open. So for the general case, if you work with the function space Cm1 or Cm, that was left open in 2011. So about a year ago, for Cm, so the general case, I guess. Is solved in the joint work with Fefferman. Okay, so let me describe how this is related to the extension problems. At first sight, it doesn't seem to have anything to do with the extensions, or with the finiteness principle in particular. So the solutions in the function space of Cm of Rn is easily described. Okay, so what we want to do is to recast this problem into an extension problem, for which we know we have the expertise to deal with. Okay, so to turn that into an extension problem, we define the following. So for each x, the Rn, we're going to look at the following set. So it consists D tuples of polynomials. Root M polynomials on Rn, such that at the point x is going to satisfy the following equations. Okay, so you can think of it as the kernel at the point x. So I will tell you why. That you should look at this set. So let particular solutions to the equation dx is equal to the sum of I of x I of x I from 1 to b. Okay, so it's just at this point it's off this system or this one equation with the unknowns in it. So any other solutions will differ from this particular solutions by something in the current. Okay, so that means.
Polynomials.
Say again.
The F's are polynomials.
The F are just real values. So this are just is an element of RT.
So why is any other solution differ by polynomials?
Well, so this is just at this point it's just a notation for the kernels. You can think of this as the kernel at the points. Right? So anything, if you look at.
Yeah, these P's are polynomials.
Yeah, so.
Yeah, but they're only vanishing at a point, so it's really.
They're only vanishing at a point.
I know, but you said any other solution to that is given by adding these P's.
Yeah.
At that point.
At that point, that's the point x.
So it's kind of superfluous to.
Yeah, it's just.
Polynomials, they're really just numbers.
Yeah.
Numbers.
They are just numbers.
Well, call them numbers then. I call them polynomials.
At the point, it's numbers.
But, well.
So.
Well, they're numbers interpreted as value to polynomials.
I think that was clever to point like that.
Okay, we wait.
Yeah.
We wait. No, go ahead.
So the original problem is equivalent to asking that whether there exists f of vectors of functions. So each component is in CFY Rn such that the f at the point x differs from the particular solutions by something in the kernel. Okay? So this is an extension property. So on all of Rn, you just ask to match this function with some error. This is the error. So it's more or less an extension problem. So this problem here is solved by a finiteness principle. So this can be answered. By a finiteness principle. Meaning that if you know how it works for finite number to point or bounded finite number to points, then you know how it works for all of Rn.
So I'm a little confused about the extension. What's the set it's defined on, and what's the data that you're trying to send?
So you're trying to find a function that matches with this given function on all of Rn. So the data is the set E is all of Rn, but the data here is this thing here.
It's already defined on all of Rn. I don't have to extend it to anything.
So you want to pick out functions from there. This is just a perfect. So at each point there, so you have to free. So at each point there, you have the freedom to move around by within there. So you have to make sure that you fit the functions through all of them, so that lies within the range, as it is in a certain smooth class. That's the constraint. The f, you don't know how regular they are to begin with. The little f.
Okay, I guess I understand that. I just didn't understand how it's an extension problem.
It feels like an extension problem. I'm not saying that it's...
Okay. I'm sorry, I tried to make it exactly the same.
Did the arbitrary geometers actually consider the problem of trying to make it zero to a certain order at the given point rather than just point-wise?
Say again?
Everyone look at the algebraic geometers.
I mean, in terms of defining the ideal, don't Kollar and so forth consider the problem?
No, they don't. They have so if you look at the papers by Kollar-C and Charles Fefferman, there are two solutions to the problems. One is analytic and the other is algebraic. The algebraic, you have to work with polynomials. So the ones that you were given here, they are polynomials. And the solutions here is that you want them to be contiguous. And you can show that the solution there are semi-algebraic. But the analytic solutions have the property that you can work with any kind of functions.
You could certainly phrase, I mean, these division problems, they come in millions of flavors. And the underlying, of course, the most...
Yeah, I think the most natural things in the for not very younger.
They don't, even this thing with no extra multiplicities already has tons of applications if they do consider it.
Okay? So the extent the decidability problem is in good shape. Let me tell you a little bit about the extension themselves. Okay, so how do you want to construct those? Okay, so usually we expect linear extensions. And if there is a finiteness principle, and the extension exists, that we expect the extensions to be sparse. Okay, so in layman terms, it means that you don't have to do too much work in writing down the extensions. So I will tell you what it means more precisely. Okay, to do that, I will have to define a few terms for you. So let X be, so this CM1 for L and P. Okay, so X restricted to the set B is the space of a restriction to the set B. So the space of functions X restrict to E, we refer to as the trace space. So automatically, anything in this function space is extendable. Extendability is not an issue. The question is how you extend it. Okay, so we would like to extend it by linear extension operators. So this is a bounded linear extension operator. So abbreviated as lineal. So linearity is that for all x in Rn, the extension of the function W can be written linearly in terms of the given function value. And it's an extension and moreover, it optimizes the norms.
Sum over E, I guess. The sum over
over E. Okay. And so if you want to check how big this norm is, it depends on some constant that depends on the function space. And the smallest possible. Okay, so that's all the almost optimum conditions. That's the extension property, that's linearity. So a bounded linear extension operator is to satisfy those conditions. Okay. So the set E, if it's arbitrary, this sum you have to make sense of it. So to make sense of it, you don't want to have too many non-zero coefficients in front of it. So sparse means that how many non-zero coefficients you have in this linear combinations. So T is T bounded linear extension operator is sparse. There exists a universal constant. Depending on the function space that you work with. finite such that when, so for all x, when it's written in linear combination of function values on the set E, the numbers of the non-zero coefficients is bounded by this constant D, independent of what x that you work with. Okay? So it's a measure of complexity of this linear combinations. Okay, so do we know such a thing exists? Okay, so did I just erase? Yeah. Okay, so if you look back at the Lipschitz extension that we constructed earlier, this is the sparse linear extension, because if you want to query the extension's value at any point, it only depends on the endpoint of the like segment. So the depth here is 2. Okay?
Sorry, I'm a bit confused about this statement.
Yeah?
Are you saying for each x, this number is less than d, but it could change? I mean, some coefficient might be non-zero for some x, but 0 for some other x.
So, for
Yes.
Yeah.
depending on this E, right?
Just depending on the x too.
Depending on the x, certainly, yeah. But but this numbers here is always bounded, independent of which x that you look at. Okay? Just like in this example, independent of which point you query it. Okay?
It works when you're emphasizing, it doesn't depend on f.
Right. It doesn't. So it's universal. Means that the only thing that is allowed to depend on is the function space that you work with. Okay. So what do we know about sparse bounded linear extension and sparse bounded linear extensions? So a result of Fefferman, 2005. Says that either B of Rn there exists a bounded linear extension operator C from Cm from Cm1 set B into Cm and Cm1 respectively. So if you work with the functions, so bounded linear extension operators almost always exist. So this is the first remark that I made. And moreover, if E is finite, then sparse bounded linear extension operators for Cm and Cm1 exist. Okay, so notice that finiteness principle is finite. So notice that in the case E is finite, if you work with either Cm or Cm1, you have the finiteness principle. So it tells you, this guiding principle here tells you that you would expect a sparse bounded linear extension operator. And this theorem sort of confirms that belief, at least for the special function space. Okay, so, and then you can ask the question, what about for infinite sets? Okay, so for infinite sets, there's no sparse bounded linear extension operator if you work with Cm. Okay, now recall that, maybe I just erased. So I told you at the beginning that there's no finiteness principle if you work with Cm and general set E. So this resonates very well with this statement here. If there's no finiteness principle, in general, you wouldn't expect sparse bounded linear extension operator. Now, what other settings do we know there is a finiteness principle? Well, so the only case that's left to check is that if you work with Cm1 for arbitrary set, we know by Fefferman's 2004 results that we always have a finiteness principle. So then you can ask the questions, can we construct sparse bounded linear extension operators? So it's a natural question. And it is true in that setting. So there exists sparse bounded linear extension operator for CM1 Rn. So I gave a talk here in 2010, so this was the result that was mentioned.
That's for all sets E.
For all set E.
Here's for finite set.
Yeah. For all E. Okay, so the business in the classical function space is well settled. What about in Sobolev spaces? Okay, so Sobolev spaces, LMT, Rn. So remember that this function space, they measure regularity in an average sense. Okay, so first of all, there's a lot of bad news to begin the analysis in this setting. So for general M, P, and N, no finiteness principles. One. And moreover, so the result due to without Petri says that there's no bounded linear extension operator for so from L11 of the plane restrict to the real line back to the whole plane. Okay, so bounded linear extension operators cannot be taken for granted.
So when you say for general M, P, and N, that's still in the range where this is a continuous function, right?
No, just any.
Well, then the problem doesn't even make sense. I mean, an element of if you've got
so you don't make sense. Of course, this problem is if you can't make sense of it, there's certainly no solutions, right? So,
but when you say general, I mean, the point is that there are a lot. That even if you set it up so that
even if you can make sense of it, there's still no finiteness principle. So it's for general MP.
But there's a way to do extension without actually evaluating at points.
Okay, so so we won't have to worry about it. If you look at the trace value, it's positive. So this is to be interpreted in the trace value sense. Okay, now we are in the bit. So we are going to functions in this function space. They're determined only up to measure 0. What we mean is that you want the function to agree with the function at the point. So you need to make some assumptions. So if for p bigger than n, then Sobolev's inequality tells you that you have derivatives up to order n minus 1 are continuous, or can be taken to be continuous. So derivatives up to n minus first order are continuous. So you can make sense of pointwise value things. But even in this setting, for p bigger than n, there's no sparse bounded linear extension operators. So this is joint work with Fefferman, Arie and Israel. 2012. Okay, so as you can see, there's a whole lot of bad news coming our way. So it's pretty, it seems pretty hopeless to say anything in general that's true in this setting. But so if you are in this good range, that is, we can identify value pointwise. What we can prove is the following. So.
And n is at least 1, I guess. You want to assume that n is at least 1, so you have pointwise values.
Say again?
You're assuming p is bigger than n,
yeah.
n, and that m is at least 1.
Yeah, m is at least 1, certain. Yeah. Okay, so. Okay, so what we proved is that for p bigger than n, So this is arbitrary. There exists bounded linear extension operators T from LMP back to LMP. So it's another trivial result in view of this counterexample here that bounded linear extension operator cannot usually be taken for granted. And in fact, we show more that so we know sparse bounded linear extension operator they don't exist. So how simple can they look? That's the next question. Okay, so this is still in Brenner. So P bigger than N, and let's say E is finite. There exists almost a sparse bounded linear extension operators T from LMP back to LMP. Okay, so what do we mean by almost a sparse? Okay, so to say that, I need to define some quantity for you. So A1 to AL, they are real value, they are linear functionals. And that. So AL here is linear combinations. So if you count the total numbers of the non-zero coefficients that appears in here, so they are called assisted quantities. If the total numbers of the non-zero coefficients is bounded by some universal constant times the numbers of points in your set E. So in other words, the total amount of work that you have to crank out of those assisted quantities is proportional to the size of the set. Okay, so how do they help? Okay, so, well, so if you want to write, so almost a sparse means the following. That this can be written as AX B F E, and then plus B I B sub X L B sub L L from 1 to L. And so E is B such that AX of B is not equal to 0 plus E is bounded by some universal constant D. Now, previously, without this assisted quantities, it was set to be sparse. So, meaning that now if you throw in the assisted quantity and still having the numbers of the non-zero terms to be controlled by a universal constant, is set to be almost sparse. So, this is the next best thing. So, let me just give you the heuristics as to what the assists are, so that you can maybe see where they're coming from. So let's say x1 to xn are real numbers. So I want you to compute their variance. So the variance can be computed in two ways. So you sum the pairwise differences squared to an average. Or alternatively, you look at the average first, and after you compute the average, you look at the expected deviation from the mean. Okay, so the advantage here is that the amount of work that you use to compute the average is on the order of n. After that, if you insert this into this formula here, computing the variance is on the order of n. Okay? Now, if you look back at this, the amount of work that you spend to compute this sigma here is on the order of n squared. So therefore, if you pre-process this quantity here, then you will have saved yourself on the orders of n operations. Okay? On a factor of n operations. So that's what they look like. So basically, what they look like is that, let's say, those are the data points. What you're going to do is that you're going to cluster them into different groups. And on each group, you're going to do the local averages. So that's what they look like. And provided the cluster, their intersection, they don't overlap too severely, meaning the number of points in the intersection is balanced. Okay, so that's what this means. That when you sum the total numbers of the non-zero coefficients in here is controlled by some constant times the number of points, meaning that the cluster, they have only a bounded number of points in it. So where do they arise? That's how they look like. They are local averages. Where do they arise? Well, they arise from solving the following simple problems, basically. So minimize. So still I give you n real numbers. I want you to minimize the following sum. Okay, so it's A. So minimize this the sum of the p's powers. So this is an easy calculus problem. If you want to solve this exactly, you just differentiate it set to zeros, so the A can be expressed in terms of the xi. Now, so you can solve this exactly, but then you have to pay the price, meaning that except for the case where p is equal to 2, which is the mean. The mean minimizes this expression exactly. So except when p is equal to 0, the expression that minimizes this quantity here is going to depend non-linearly on the xi. Now, we are looking for linear extensions. So every problem that we encounter along the way, this is a subproblem that we will encounter along the way, we will have to concur it linearly. Okay? So, but we are not so much interested in minimizing things exactly. We can afford to lose a factor. So if you want to minimize up to a factor, you can do the following. So let A be the mean. Then you insert this into the expressions. Well, it's not going to give you the mean exactly. So A is 4. But you're going to minimize it up to a universal constant, meaning that it's independent of the number of points in this expression. So if you use this, that's the assisted quantity, that's how they arise, and that's what they look like. So I hope that I will give you a sense as to what the statements say here. Okay? All right, thanks.
Do you have any more questions for the speaker?
I noticed you didn't mention the Holder spaces CM alpha, where alpha is between 0 and 1.
It's the same. It's no different if you look at it for alpha equals to 1 or alpha different from 1. And in fact, you can look for a more general class of function space in which the alpha is actually a function.
So in particular, there's no trouble to do this with CM alpha.
As long as you give me a little bit more regularity to better than CM, I can do the statement will still be true. Yeah.
Other questions? I'm going to thank your speaker again.